Greetings, AP Chemistry. This is Mr. Harper with the second overview podcast from Chapter 14. This is going to cover colligative properties mostly. I'm going to explain again what they are and the mathematical equations that we can use with them. Okay, so really quickly, guys, what colligative properties are. The colligative properties, if I say the word colligative properties to you, or the phrase rather, what these are is they're properties of a solution that are different from those of a pure solvent, okay? Now, really what these are, okay, if we consider a solvent, like, for example, water, okay? Water has certain physical properties. It has a defined freezing point. It has a defined boiling point. These are both properties of water. Now, when we dissolve a solute in water, it changes the freezing point, and it changes the boiling point. These are examples of colligative properties because they are changed by the presence of the solute, okay? And the degree to which the properties of a solvent changes only depends on the number of solute particles that are dissolved in the solvent, not on the identity of the solute particles, okay? So these are the properties that we're going to look at that are changed by the presence of a solute. The first is vapor pressure. The vapor pressure of a pure solvent is reduced by the presence of a solute. Okay. The boiling point of a solution is changed. That's elevated. It's called boiling point elevation. Okay. The freezing point changes. It gets lower. That's called the freezing point depression. And the last is osmotic pressure. There's a separate podcast governing osmotic pressure, so we're not going to talk about that here in this podcast. We're going to focus on these three right here. Okay. Now, once again, guys, the really important thing here to remember is that these properties depend only on the amount of solute present. So we're just looking at the amount of solute, not the identity of the solute. It doesn't matter what it is, just matters the number of solute particles that are present. Okay. So the first thing we're going to talk about here is vapor pressure. Okay. And we're going to start here with an interesting illustration. Here we have two pictures. Here on the left, okay, let's look at this one first. What we have here is two beakers filled with liquids that are put inside a bell jar. Okay, this is called a bell jar. Okay, the beaker here on the left is just pure water, and on the right we have an aqueous solution. And initially at time 0, okay, these both have the same level of liquid in each of the beakers. Now, if we let these sit for a while, what's going to happen, what you will observe, is that there's a net transfer of water molecules here from the beaker on the left over to the beaker on the right. And if we let this sit long enough, what we're going to see is this. The beaker here on the left eventually will be empty, and the beaker on the right is eventually going to have a higher level of the liquid. If we compare the level of the liquid there to the level of the liquid here, it has changed. It's actually all transferred from the left into the right. Okay? Now, let's think about the reason why this is, okay? If we, and this is a different diagram we're going to use to explain why this phenomenon occurs. Here on the left, we have a container containing pure solvent. On the right, we have a solution with a non-volatile solute. Non-volatile means that it does not vaporize. So this doesn't vaporize, it does not contribute to vapor pressure, okay? So, if we consider what's happening here on the left, we have, at any given point in time, guys, if this is a pure solvent, we're going to have some of these solvent molecules with sufficient kinetic energy to exit into the gas phase. Okay, so some of these are going to be vaporizing at any point in time, and some of these solute molecules will be going back into the liquid phase. Okay, now, because these gas molecules up here are flying around, they're colliding with the sides of the container, they are going to exert pressure on the sides of their container. The pressure that this exerts is called vapor pressure, okay? Because it's the vapor coming off the liquid that is colliding with the walls of the container and exerting pressure upon the walls of the container, okay? Now, if we look up here at the gauge, and we don't know, I don't know what units this is supposed to be in, but let's just call this 3, torr, for the sake of argument, okay? Here's our pure solvent. It's exerting a vapor pressure of about 3 torr, let's just say for the sake of example. If we look here on the right, the vapor pressure being exerted by the solution, where we have a non-volatile solute dissolved, is less. This is about 2 torr, if we look at the gauge. Now, let's think about the reason why that is, okay? If we consider here the solution, we can see, according to the diagram, that there are fewer solvent molecules here that go into the gas phase as compared to the pure solvent. Now, why is that? Well, in order for the solvent to vaporize and go into the gas phase in the first place, we have to have solute molecules that are on the surface, or solvent molecules rather, that are on the surface of the liquid. Okay, and we know there's going to be a certain fraction of these that have sufficient kinetic energy to move into the gas phase at any point in time. If we look here at the surface of the pure solvent and we compare that to the surface of the solution, we can see that there are fewer solvent molecules at the surface in the solution. Because there's fewer solvent molecules at the surface here in the solution, that means there's less of a chance at any point in time for some of these solvent molecules to move into the gas phase. This doesn't happen, it can't happen as much. Because of that fact, okay, because there's less solvent molecules that can make it into the gas phase, there'll be less molecules in the gas phase, and they're going to exert a lower vapor pressure. And that's why a solution has a lower vapor pressure than a pure solvent, okay? And so we go back to this picture we had over here. If we imagine what's happening at any point in time within these two beakers, with the water, we have some molecules that are going into the gas phase and some that are going back into the liquid phase, okay? But over here, that's happening slower, okay? So basically what's happening is the water vaporizes faster than the solution does, and these water molecules are able to enter into the liquid phase over here, and so because of that difference in rates, eventually all the water transfers from this beaker into this beaker over there. It's fascinating stuff, okay? Now, we can mathematically relate the vapor pressure of a solution and the concentration of the solvent, essentially, using Raoult's law, okay? Now, there's a couple statements that we're going to look at. So, here we go. The vapor pressure of a solution, okay, the vapor pressure exerted by a solution is going to be the mole fraction of the solvent times the vapor pressure of the pure solvent, okay? What this little degree sign here means is this is the pure solvent right here, okay? So if we have a solution, the vapor pressure exerted by the solution is the mole fraction of the solvent times the vapor pressure that would be exerted by the pure 100% solvent, okay? Now, this statement of Raoult's law is assuming that the solute is non-volatile and that it does not contribute to the vapor pressure of the solution. Or in other words, if the solute is a solid, like sodium chloride or sugar or something of that nature, okay? There's a different way we can say this for two or more liquids. In the case that you mix two or more liquids, what that means is that the solute does contribute to the vapor pressure. Okay? This is important to take into account. So, for example, if you have an aqueous solution of ethanol, ethanol is a liquid that is volatile and will vaporize and contribute to the vapor pressure. Okay? In that case, the vapor pressure of the solution is equal to the mole fraction of component A times the vapor pressure of pure liquid A plus the mole fraction of component B times the vapor pressure of pure liquid B. And, you know, so you can add more terms if you had to, if there's a multiple component system, whatever. But that is how you can calculate the vapor pressure using Raoult's law, okay? So this is a graph, okay, guys. Well, the top part here evidently got cut off on the PowerPoint, but what this is showing you here is how the vapor pressure of a liquid varies with the temperature, okay? So what this should have here on the x-axis, except it's cut off here on my PowerPoint, is this should be temperature, and what we have here on the y-axis is the vapor pressure in millimeters of mercury, okay? And here this red line is for pure benzene, and the blue line represents benzene with a solute dissolved in it. So this is a solution, okay? Now, what you can see from this is that if we look at this particular temperature right here, okay, at whatever temperature this happens to be, I don't know what it is exactly because the temperature's cut off, but here's the vapor pressure of pure benzene at that temperature. If we add a solute, we can see that the vapor pressure of the solution is going to be lower, okay? If we look here at the y-axis, it's going to be lower. And that's going to be true at every temperature. Now, that has some implications. Remember, guys, we said that that boiling point, okay, or in other words, normal boiling point, okay, the normal boiling point of any solution is where the vapor pressure is the same as the atmospheric pressure. So in other words, when the boiling point of a liquid is where the vapor pressure is equal to 1 atmosphere. That's the normal boiling point, okay? Now, what that means, if we look at pure benzene, okay, this is going to have a certain, the dotted line here is showing you the normal boiling point of pure benzene. I forget what that is, but that's, roughly 72 degrees Celsius or something like that. That's the normal boiling point of pure benzene. When we add a solute, okay, and this is the point, by the way, guys, where the vapor pressure is equal to 760 millimeters of mercury or 1 atmosphere of pressure, okay? Now, for the solution, because the vapor pressure exerted by the solution is lower at any given temperature, what that means is that in order for the solution to boil, it's going to have to go to a higher temperature because the vapor pressure that it exerts is lower at any given temperature. So we have to raise the temperature somewhat, and we can see there's a shift here in the temperature at which the vapor pressure of the benzene solution is 760 millimeters of mercury. In fact, in this particular example, it's gone up by 5.1 degrees Celsius. So the boiling point of the solution is going to be higher. And this is going to be true of any solution. The boiling point of a solution will always be higher than that of a pure solvent. And that effect is called boiling point elevation. Okay? And let's consider an example here really quick. If I go visit my sister in Denver, Colorado, okay, I was there this summer. The atmospheric pressure in Denver, Colorado is lower than it is here. It's, I don't know what it is, we'll just guesstimate here. It's about 0.9 atmospheres. It's lower than it is here. And so in Denver, Colorado, when we're at this higher elevation, when we have a lower atmospheric pressure, pure water boils at roughly 93 degrees Celsius. I measured this with a crude thermometer while I was there this last summer. Now, when my sister boils something, like an egg or something, what she does is she tosses salt in the water. The reason why she tosses salt in the water is because that has the effect of raising the boiling point of the water. So her salt water solution boiled at roughly 105 degrees Celsius. The boiling point went up due to the presence of the solute, okay? The boiling point of a solution is always greater, always greater, or you could say higher, okay, at a higher temperature than that of a pure solvent, okay? And this effect depends on the concentration of the solution. The more solute we have, or the higher the concentration, the higher the boiling point of the solution is going to be, okay? The reverse happens with freezing point, okay? If I take pure water, this we know normally has a freezing point of 0 degrees Celsius. Now, if I want to make ice cream, okay, if you guys have ever done this at home, you will know that when you make ice cream, you add rock salt to the ice. The reason why you do that is because when you add the rock salt to the ice, that causes the freezing point to go down, and that ice is actually going to become the ice temperature is going to decrease. If I add enough rock salt, you can actually get the freezing point down to negative 15 degrees Celsius or so. The freezing point goes down, we add a solute. This effect is called freezing point depression. Not because the freezing point gets sad, but because it goes down, okay? The freezing point of a solution is always lower, all the time, than that of a pure solvent, and the more concentrated the solution is, the lower the freezing point gets, okay? There's some formulas that we can use to mathematically describe freezing point and boiling point and the changes due to the presence of a solute. So here's the boiling point elevation formula. It looks like this. Delta T, BP, is equal to I times molality times KBP. Okay? Now, what these terms are right here, okay, delta T BP, this is going to be the change in boiling point. Okay, it's the change in the boiling point. It's going to be in units of degrees Celsius usually. I is called the Van Hoff factor, which we'll describe here in a moment. M here is going to stand for the molality of the solutes, okay? So it's telling you the concentration in moles per kilogram of solvent. And this is just a constant, okay? And this is found in your textbook in chapter 14. Freezing point depression has a very similar formula. Delta T Fp is equal to I times M times K Fp. This looks very similar. I and M have exactly the same meaning. I is the Van Hoff factor. M is the molality of the solute. Delta T Fp is the change in the freezing point. And KFP, this is just another constant, which is characteristic of, the solvent that you are working with, okay? Oh, excuse me, got the hiccups. These are found in chapter 14 of your textbook, okay? So we're going to look at some examples of how to use these formulas and some applications, but first let me describe to you what is the Van Hoff factor, okay? What is the meaning of I? I stands for, or corresponds to, the number of particles, okay, that are produced when something dissolves. So, for example, if we look at sodium chloride, okay, when we dissolve 1 unit of sodium chloride in water, we actually get 2 ions out, sodium plus chloride, okay? In this case, the Van Hoff factor, I, is equal to 2. If we have something like calcium chloride, CaCl2, okay, when this dissolves in water, we get a calcium 2 plus ion, and we get 2 chloride ions. In this case, the Van Hoff factor I is 3, because for every unit of this that we dissolve, we get 3 ions. In a similar fashion, say we had titanium 4 chloride. When this dissolves in water, we get a titanium 4 plus ion, plus 4 chloride ions. In this case, the Van Hoff factor I is going to be 5, because for every unit of titanium chloride that we dissolve, we're going to get 5 different ions, okay? I hope you guys see how that works. That's the Van Hoff factor. So it tells us how many particles we get, really, when something dissolves, because when we're talking about boiling point or freezing point, it only depends on the number of particles, okay, that we have in the solution. When we have ionic compounds, the particles are the ions. Now, say we have something like sugar. I'll just call it glucose, C6H12O6. If we dissolve that in water, what happens? The answer is absolutely nothing. It doesn't break up. It does not dissociate. So we get 1 C6H12O6. For any covalent molecular solid, the Van Hoff factor I is going to be 1 because it doesn't dissociate or break up into parts. Okay? There we go. Now, these are all ideal. Okay? In the ideal case, ions totally dissociate in water and break up totally and completely into ions to the extent that they dissolve. And this is ideal behavior. If the problem doesn't say anything else, assume that things behave ideally. But know that this is most true. Okay, this idea that we're showing here is most true for dilute solutions. Okay, as the solution becomes higher and higher and higher in concentration, you're going to deviate somewhat from ideal behavior, and let me explain why. There's an effect called ion pairing. So say, for example, we have something like 6 molar sodium chloride. 6 molar sodium chloride is pretty concentrated, okay? Normally, guys, we assume that the sodium chloride is going to break up, and we're going to have sodium ions, and we're going to have chloride ions that are separate in solution. We assume that they break up and fly their separate ways entirely. But when we have a very high concentration of the ions in solution, these can actually find each other again, and they're going to be attracted to each other. Now, they don't reform the solid, but they may clump together because this positive ion is attracted to this negative ion. They can kind of clump together and go together. When that happens, this effect is called ion pairing. Okay, and when this happens, the Van Hoff factor, I, is actually going to be less than the ideal case. Now, in reality, the Van Hoff, I is always less than the ideal value because this will always happen to some extent, but the effect becomes more pronounced the more concentrated the solution becomes due to this ion pairing effect because they don't completely separate from each other. Unless you're told otherwise, assume they behave ideally, but know that in reality, the Van Hoff factor I will always be less than the ideal case due to the ion pairing effect, and that the deviation from ideality or from ideal behavior will become greater the more concentrated the solution is. Okay, so let's skip that and do another example. Let's do an example here. We're going to determine the vapor pressure, the boiling point, and the freezing point of a solution made by dissolving 1,840 grams of this right here. This is ethylene glycol. And you may recall that this is the main ingredient in antifreeze, to 5.50 kilograms of water. Okay, so in this case, water is going to be our solvent. And because vapor pressure depends on temperature, let's say we are working at a temperature of 25 degrees Celsius. Okay, and let's just kind of do this in order. Let's do vapor pressure first. Okay, to calculate vapor pressure, the vapor pressure exerted by a solution is equal to the mole fraction of the solvent times the vapor pressure exerted by the pure solvent at that temperature. Okay, so in order to figure this out, we need to know what the mole fraction of water is in our mixture. Well, let's change 5.5 kilograms of water into moles. If we do that, 5,500 grams divided by 18 is about 305.6 or something moles of H2O. Okay, let's change 1,840 grams of ethylene glycol into moles also. Let's just total this up real quick. Ethylene glycol will be about 17 plus 24 is 41, plus 4 is 45, plus 17 is 62 grams per mole. So 1,840 divided by 62 is approximately, we'll say 29.68 moles. Okay? In that case, guys, the mole fraction of the H2O is going to be 305.6 moles of water divided by the total number of moles, which is 305.6 plus 29.68. So if we just calculate that real fast. Okay, we'll say about 335.28 moles. And if we go through and calculate that, okay, 305.6 divided by 335.28, we get 0.911. Of course, keeping track of the fact that this is an insignificant number, and so we'll only have three sig figs. 0.911 is the mole fraction of water. Okay, so we're going to plug that in. 0.911 is the mole fraction. Now we're going to multiply by the vapor pressure of the pure solvent at that temperature. We're going to find the vapor pressure of the pure solvent, guys, is in your textbook in the appendix. So hold on one second. Go ahead and look that up for yourself and plug it in and pause the podcast while you do so. Okay, guys, we're back. If you look at the vapor pressure of pure water at that temperature, you'll see that it is about 23.8 torr, or millimeters of mercury, an equivalent measurement. Okay, if we go through and calculate that, we get 0.911 times 23.8, and it is 21.7 torr is the vapor pressure of the solution. Notice, guys, it is less than that of pure water at that temperature. Okay, let's do now the boiling point. Okay, the boiling point of normal water is 100 degrees Celsius. So what we're going to do is we're going to calculate the change using the equation that we gave before. So delta T BP is going to be equal to I times the molality of the solute times K BP for water. This constant is characteristic of each individual solvent. Each one has a different kBP value. This is given in chapter 14, and let me find the table here really fast. That's on page 673 of your book. Okay. Now let's just fill in what we know, guys. For ethylene glycol, this is a covalently bonded molecular compound. It is not going to dissociate, so I in this case is just going to be 1. Now we need to know what the molality of the solute is. Well, we have here 29.68 moles. To calculate the molality, we would divide that by the kilograms of water, which is 5.50 kilograms. And if we go through and calculate that really fast, 29.68 divided by 5.5 is about 5.40 molal. Okay, so we're going to plug that in here. 5.40 molal. And we're going to multiply this by the boiling point elevation constant found on page 673. In this case, it's going to be a positive 0.5121, and it is degrees Celsius per molal is the units. Now notice, because molal here is in the denominator, that will cancel out. Now, of course, you're going to ask me, Mr. Harper, do I have to show the units? And the answer is yes, you always must show the units. Okay, and so we're going to go through and multiply. 5.4 times 0.5121, blah, whatever, is 2.77 degrees Celsius. Now, what does that represent? This is the amount by which the boiling point is elevated. So, since the normal boiling point of water is 100 degrees Celsius, the boiling point of the solution is going to be about 102.77 degrees Celsius or so. So, there we have it. That is the boiling point of the solution. To find the freezing point, we're going to do something analogous. We're going to use our freezing point depression formula. So, delta T Fp is equal to I times M times K Fp. I again is 1. The molality of the solute is 5.40 molal. And now we're going to use the freezing point depression constant, also found on page 673 of your textbook. And for water, that has a value of negative 1.86 degrees Celsius per molal. Now, what the negative means is that the freezing point is going to go down when we have the solute dissolved, so molality here is going to cancel out. And if we go through and we multiply 5.4 times 1.86, yeehaw, so it's going to go down by negative 10.0 degrees Celsius. Since the normal freezing point of water is 0 degrees Celsius, this is going to be our new freezing point, negative 10.0 degrees Celsius. This is, again, guys, why you put antifreeze in your car, is because that lowers the freezing point of the coolant, and that way when it's cold outside, your car does not, or your radiator, rather, does not freeze. So there we have it, guys. That's the application of these formulas. Now, that's an easy usage of them. Let's look at something that an important application, this is what we did in the lab, guys, was to determine the molar mass of an unknown compound. Okay, back in the days before mass spectrometers, people used to use colligative properties to determine the molar mass of an unknown. In fact, this is still done in labs today, usually with osmotic pressure, but sometimes with freezing point depression. Let's consider an example. It says an aqueous solution. So an aqueous solution meaning that we have water as our solvent, contains 0.180 grams of an unknown non-ionic solute and 50 grams of water. The solution freezes at negative 0.04 degrees Celsius. What is the molar mass of the solute? Okay, so here we want to find molar mass. Now, let's just keep in mind, guys, if we want to find molar mass, what are the units of molar mass? This is something that a lot of people seem to have forgotten. Molar mass has units of grams per mole. So if I want to find the molar mass of a substance, so that's what I'm trying to find, the molar mass of an unknown, what I need to know is the mass of the sample and the number of moles that corresponds to. We have the mass of our sample. It's 0.180 grams of the unknown. We know how much mass that we have. What we need to find is the number of moles, okay? So we have freezing point depression data, so it makes sense here to start with our freezing point depression formula. Delta T Fp is equal to I times M times K Fp. Now we know that this is a non-ionic solute, meaning that I is going to be 1. That's what that tells us. I is 1. So we can just sort of ignore this. I don't know yet the mole. I can't solve directly for the moles, but I can solve here for molality. So let's do that. The molality of the solution is going to be the change in freezing point, delta T Fp, divided by KFP, okay? If I go in and plug in what I know, the change in freezing point is negative 0.040 degrees Celsius. For water, KFP has a value of negative 1.86 degrees Celsius per molal. The degrees Celsius is going to cancel out, and I'm going to get the molality of the solution. 0.04 divided by 1.86 gives me 0.0215 moles of the solute per kilogram of water. Okay, per kilogram here of our solute. Now, I know how many grams of water I have, right? I have 50 grams. If this is how many moles I have per kilogram, well, how many kilograms of water do I have? I have 0.050 kilograms of water. If I multiply here, the kilograms of water is going to cancel out, and this is going to tell me how many moles of my substance I have. So multiply by 0.05. Okay, we have of this compound 0.00108 moles. Okay, that's how many moles of the compound we have now. To find molar mass, I need to know grams, I need to know moles. I know the number of grams that I've got. I've got 0.180 grams of the compound. That corresponds to 0.00108 moles. If I go through here and I do the division, 0.180 divided by 0.00108 gives me 167 grams per mole. And there we go, guys. That's the molar mass of the compound. And this is one way you can in real life use another tool in our tool belt here, so to speak, to find molar mass of an unknown compound. So there we have it, guys. That is the end of the overview 2 from chapter 14. Use that to review and use that to complete problems dealing with colligative properties. And hope you're having a good break, and I will see you when we get back. Goodbye.